Alright, so today we are covering a discussion of automorphisms of root systems that we kind of alluded to a bit earlier in the last video. And this is going to be largely based on our previous discussion of the isomorphism theorem we developed last time. An automorphism by the isomorphism theorem. Our results from last time. An automorphism of our root system determines an automorphism of our maximal Torel subalgebra, which can be extended to our entire space. For example, the map sending each root, I guess we'll call this root, so we should use alpha. Because we know every root has an inverse, the map of inverses is going to be an easy automorphism, which is guaranteed. This belongs, of course, to the automorphism group of our root system. And it's going to induce, obviously, h to negative h on our maximal Torel subalgebra. I guess we won't do this as a parenthetical, we'll just write this. So if we have a map sigma from h to h, so sigma of our h of alpha is then going to be equal to negative alpha, which is h of negative alpha. So we are going to decree, going to send each x alpha to negative of y alpha. With the unique z in L alpha such that the bracket of negative y alpha and z is h negative alpha is x of negative alpha. Then sigma extends to an automorphism of L, sending x alpha to negative y alpha. Making, by our previous result, that y alpha is sent to negative x alpha. Also, sigma obviously has order 2. Sigma squared fixes the generators of L. Use our proposition. So our L is, as before, not necessarily simple. Fix x alpha in L alpha. Let y alpha in L negative alpha such that bracket of x alpha and y alpha is h alpha. Then there exists an automorphism of L of order 2 such that sigma of x alpha is negative y alpha, sigma of y alpha is negative x alpha, and sigma of h is negative h. We've already seen this before for the two-dimensional special linearly algebra. Okay, one second now, things are happening. It's the end of our proposition. The file group accounts for most of the automorphisms of a root system. Keep in mind, remember our discussion before with the Dinkin diagrams and the diagram automorphisms? A previous theorem assures corresponding automorphisms on our full group L, which extend the action of the Weyl group on our maximal toral subalgebra. If sigma is a symmetry in the Weyl group, then the extension of our sigma to an automorphism of L must map the root space of a beta to the root space of the image of that root beta under sigma. You can also give a direct construction of such an automorphism by our previous discussion, which I think we closed off last video with. And we only need to do this for the reflection of a root, which generates the Weyl group, and the collection of all reflections, right? Since the adjoint of x beta for beta in a root system is nilpotent, we can define the inner automorphism taf of alpha as, recall, the exponential of the adjoint of x alpha flanking the exponential of the adjoint of negative y alpha. With, of course, the bracket of x alpha and y alpha being h alpha. And we want to know how this acts on our maximal toral subalgebra. So we're going to write h as the direct sum of the kernel of our root alpha, and F, and our field scaling up our copies of H alpha. Then taf alpha of H has to be H. For all H in our kernel. And taf alpha of H alpha is going to be negative H alpha. Which means that taf alpha and sigma alpha agree on H. So taf alpha sends the root space of beta to the root space of the image of beta under sigma alpha. But we note here that if we represent our reflections, and hence our vowel group, as elements of the identity of L, does not lead to the vowel group in general being a subgroup of the interior automorphisms of L. Alright, so that's actually that one chapter. I kind of ended it at an awkward point last time, but that was kind of just how it panned out. Next up here, we're moving on to the Cartan subalgebra. Cartan subalgebras is our next topic. So in this previous section here, we showed that the pair of a semi-simple Lie algebra and its maximal torus subalgebra is determined up to automorphism. I mean isomorphism, not up to automorphism doesn't make any sense. Up to isomorphism by its root system. However, this still leads to a dependence on our choice of H. Because if we pick a different maximal torus subalgebra, we could possibly not recover. Of course, by this, if we have the same maximal torus subalgebra, we're going to get the same semi-simple algebra that is containing it, but the root system is not necessarily going to be the same. So we don't know yet. So we know that our root system determines our semi-simple Lie algebra, but we don't know yet that our semi-simple algebra determines our root system. So we don't have we want ideally a bijection between semi-simple Lie algebras and root systems. And we have a way to get not necessarily to construct explicitly, but to implicitly get our semi-simple Lie algebra from the root system, but not the other way quite yet. So for example, the fact that the dimension of our Lie algebra is equal to the rank of our root system plus the cardinality of our root system cannot distinguish BL and CL as Lie algebras. We will eventually show, and that I think I mean in a later chapter, that all maximal toral subalgebras of L are conjugate under the automorphisms of L. This will be done in a later chapter, but in the wider context of an arbitrary Lie algebra where the appropriate analog of our maximal toral subalgebra is a Cartan subalgebra. So we're going to generalize things a bit first. And this also says here, F may be of arbitrary characteristic but still needs to be algebraically closed, although it says you can kind of get rid of this. I'm guessing in a way kind of like Barbaki style with the whole change of base. It says for the main results, it's enough that the cardinality of our field shouldn't be like too small in quotation marks relative to the dimension of our algebra, whatever that means. Alright, so our next topic here is decomposition. Let's write it in full since it's a chapter title. Decomposition of our algebra L relative to the adjoint of X. So recall that if T is an element of the endomorphisms of a finite dimensional vector space, then V is the direct sum of all, I'll write a new line, VA being the kernel of T minus A on 1 to the power of M, where M is the multiplicity of A as root of the characteristic polynomial of T. Each VA is invariant under T with the restriction of T to VA as the sum of the scalar A and a nilpotent endomorphism. So the idea is that we apply this to the adjoint representation of an element x. Which, I mean, that's good, the whole chapter title, I guess. So we're going to write our L as the union across A being elements of our field of such LA of our adjoint of x, which is L0 of the adjoint of our x, plus what we're calling L star of the adjoint of x, with L star, the adjoint of x, being the direct sum of A and F non-zero of these LA adjoint x. So essentially it's everything that L0 doesn't cover. Fortunately, if K is a subalgebra stable under the adjoint of x, we can write K as K0 of the adjoint of x plus K star of the adjoint of x for K in anywhere in L, not even just in X. This leads us to a lemma. For A, B, and F, the bracket of LA on the adjoint of X, and with LB of the adjoint of X, it's going to be contained within L of A plus B of the adjoint of X. We also see from this that L0 of the adjoint of X is a subalgebra, and when characteristic of our field is 0, for each non-zero A, each element of LA of the adjoint of X is adjoint nilpotent. Now, earlier, I believe we proved a formula. It's something like this: adjoint of x minus a minus b to the m on the bracket of y times z is the sum for I from 0 to m of m choose I times the bracket of the adjoint of x minus a to the I on y times the adjoint of x minus b to the m minus I of z. All terms on the right hand side are 0 for large M. So y is an LA of the adjoint of x, and z is an LB of the adjoint of x. Next up, our next topic here is engel subalgebras. We just saw that L0 is the adjoint L0 is a subalgebra. So we're going to call L0, each L0 adjoint of some x, an engel subalgebra of L. We then get a couple of lemmas to go along with this. The first lemma, let K be a subalgebra of L. Choose Z and K such that L0 of the adjoint of Z is minimal in the collection of all engel subalgebras of all L0 adjoint of X for X and K. Suppose K is inside of some L0 of adjoint Z. Then L0 of adjoint Z is within L0 of the adjoint X for all X and K. Proof. So we're going to fix a arbitrary X and K. Consider the family of endomorphisms of the form the adjoint of Z plus Cx for C in our field. And the endomorphisms of L. Since K0 is equal to L0 adjoint Z, is a subalgebra of L including K. These endomorphisms stabilize our K0, and so induce endomorphisms of L over K0. If T is an indeterminate, we can write the characteristic polynomial of this adjoint, of each adjoint of Z plus C of X as the product of F on T with C of G on T with RC. Which is a product of characteristic polynomials on our K0 and our L over K0. If R is the dimension of K0 and N is the dimension of L, we can write F of TC as the sum from 0 to R FIC with F0 being 1 of T to the R minus I. and g of t, comma c as the sum from 0 to n minus r of f sub I c t to the n minus r minus I with, oh, this should be a function g, it's not the same f. With f0 equaling g0 equaling 1. And we can see the coefficients of each fi, c, and gi of c all are polynomials in C of degree less than or equal to I. We also see that the next we see that the eigenvalue 0 of the adjoint of Z occurs only on our K0. So our Gn minus r is not identically 0 on F. Thus we can find scalars which are not non-zero scalars. Okay, sorry, the wording is here weird. The wording is weird here, I'm saying it weird. Scalars which are not zeros of g to the n minus r. Say ci from 1 to r plus 1, distinct. To say that Gn minus r of some c in here is non-zero is just to say 0 is not an eigenvalue of the adjoint of z plus cx on our quotient space L of k0. So all of our L0 of the adjoint of z plus cx lies in the subspace K0. As K0 is minimal by choice, L0 of the adjoint of Z is equal to L0 of the adjoint of Z plus Cix for all I in the interval of 1 to r plus 1. So the adjoint of Z plus Cix has only the eigenvalue 0 on our L0 of the adjoint of Z. So ft of Ci is equal to just t to the r. So each of our polynomials fi from 1 through r Each of degree, if we recall, at most r, has r plus 1 distinct zeros. And so r0. Thus, RL0 of the adjoint of z plus cx is within our k0 for all c in F. Now, x is arbitrary, so if we replace x with x minus z and let z equal 1, then we get that L0 of the adjoint of x contains L0 of the adjoint of z. Brings us to a second lemma. If K is a subalgebra of L containing an engel subalgebra, then the normalizer in L of K is just K. So engel subalgebras, we get trivially from this, engel subalgebras are self-normalizing. And the proof. Say K contains L0 of the adjoint of X. Then adjoint of X acts on the normalizer in L of K over K without eigenvalue 0. As K in X implies the normalizer of an L of K bracketing with X being within K, adjoint of X acts trivially on our NL of K over K. So K must be equal to NL of K, the L normalizer of K. And we're done that chapter. And we're a little under time, but things might be happening, so I think I'm going to call it here for our current video. I'm kind of changing up my setup a little bit. Probably won't be too noticeable for you guys then. Maybe how I speak a little bit will be different, but other than that, yeah, this is what we're going to keep on. We're going to be in here for a while, I think, this kind of talk. I think that's fine.